Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So today, what we're going to do is we're going to press forward in Chapter 7. We're going to use Laplace transforms. Transformations. We're going to use them on initial value problems. So transformations of initial value problems. That's the topic. So in order to be able to apply the Laplace transforms to derivatives, in particular differential equations, what we are going to need to do is have a couple of conditions satisfied. And first, let's just define what those conditions mean. So a function is piecewise smooth if it is differentiable, meaning its derivative exists, on all but a finite number of values. So examples of this would be basically everything that we have known and loved, except for such things as maybe a tangent, things like that. And then a function is of exponential order as t goes to infinity if there is a c such that the limit as t goes to infinity of e to the negative ct f of t equals 0. So in other words, the function grows slower than the exponential function, so it gets smothered by a negative exponential function. So setup for what is going to happen next is that we're going to have a function that is both of these things. F is piecewise smooth and of exponential order on the interval from 0 to infinity. Then there is a c such that and now the Laplace transform of f prime of t, this is the big result, is equal to the Laplace, s times the Laplace transform of just the original f of t minus f of 0 for s greater than that c, for s greater than c. In other words, the Laplace transform of f prime of t is equal to s times f of s minus f of 0, writing it in the more standard notation of a capital letter with the letter s as the variable for the Laplace transform. Well, to prove this, let's have a look at what this actually would mean. So the Laplace transform of the derivative f prime of t, by definition, that's equal to the integral from 0 to infinity of e to the negative st f prime of t dt, but this can be handled by integration by parts, where u is equal to e to the negative st du. Since s is a constant from the perspective of t, this is just going to be negative s e to the st, sorry, negative st, and then here v is going to be, sorry, dv is going to be f prime of t dt, which makes v itself just f of t. So then, under this integration by parts regime, we would have uv, which is going to be equal to e to the minus st f of t, and that's going to be going 0 and infinity, minus a negative, so it's going to be plus s times the integral of v du. So that's going to be, I just pulled the s out because it's a constant in respective of t, negative st f of t dt from 0 to infinity. But here, this is going to be 0 when we plug in infinity, and that's by the assumption that it is of exponential order, minus, and then here what we're going to have is 0 plugged in is going to be just 1, and f of 0. And then this is the same as the definition of just the Laplace transform of f times that s. So then that, in turn, by just a slight rearrangement, is going to equal s Laplace transform f of t minus f of 0. Okay. So there it is, established in black and white that this is true. But how do we actually make use of this? This is where the whole purpose of Laplace transforms is now going to come into focus. So the use of this is actually what makes Laplace transforms even a part of this class. So now let's see how to actually apply this. Okay, now the first major thing we're going to have to do in order to make this more usable is explore what it's going to mean for higher derivatives. So let's think about what it would mean if we took the Laplace transform of the nth derivative of f of t. So Laplace transform fn of t. Well, the nth derivative, that's really the same thing as just the derivative on top of n minus 1 previous derivatives. So what we are in now is the setup of the previous problem, where what we have is the derivative of something in here. So what that means is it's going to be s times the Laplace transform of the something in here, which now is going to be fn minus 1 of t minus f, that's going to be the something in here evaluated at 0. But then we would just repeat. And what we've got here is s times, and then it's going to be s times the Laplace transform of f n minus 2 of t minus f n minus 2 of 0 minus f n minus 1 of 0. And if we distribute that s, that's going to be s squared Laplace transform f n minus 2 t minus s f n minus 2 at 0 minus f n minus 1 at 0. Now, that's enough for us to start to see the pattern of how this is going to develop as we take more and more derivatives. The first term is going to have a higher and higher power of s, and then notice the powers of s count down here. Meanwhile, this is a higher derivative, a lower derivative, and the lowest derivative. And so ultimately, if we repeat this n minus 2 more times, we'll end up canceling out all the other derivatives, and we're going to have n as a power here, so s to the n. So this is like repeat n minus 2 times is what's happening here. So this is going to be Sn Laplace transform of just the f now. Minus all but one of those s's times f, and then here it's just going to be the f of 0, so just this one right here, the innermost one, minus minus s times n minus 2 f prime of 0 minus dot dot dot, and then we'll just keep counting down until we run out of s's, and at that point we'll be at f n minus 1 at 0. So concretely what this means, so if x of t if x of t, the Laplace transform of that is equal to just capital X, and we will just write it as just a capital X, not we won't write the s if we can help it typically, then something like x third derivative, something like that, will end up looking like s to the third times x, and then minus, and then we're going to have s squared, and it's going to be x of 0, and then we're going to have minus just s times x prime of 0, and then we're going to have minus just x double prime of 0, for example. Now, supposing we want to apply this to an initial value problem, here's how it's going to work. So here's the idea. So we're going to take the initial value problem, we're going to apply the Laplace transform to both sides. Then we're going to solve for x, like the capital X, the x that is the Laplace transform. Then we're going to apply the inverse Laplace transform to both sides to get x of t. Okay, so let's actually give this a try, and as an example, let's try it with, let's try it with this. So as an example, let's take the initial value problem x double prime plus 9x equals 0, where x of 0 is going to equal 3, and x prime of 0 is going to equal 4. Alright, well, we've got to take the Laplace transform of both sides. So it's going to be the Laplace transform x double prime plus the Laplace transform of 9x is equal to the Laplace transform of 0, which is just going to be 0. And now we just apply what we just found. So second derivative means it's going to be an s squared times x minus s times x prime, or sorry, x of 0. So s times x of 0 minus x prime of 0 plus 9 times, and then here the x is just going to be x. Alright, and now our goal here at this point is to solve this for the x and also plug in the numbers. So this is going to be s squared x minus, and then it's going to be 3s minus 4 plus 9x equals 0. So we're going to move all the terms that have the that don't have an x to one side, and all the ones that do will stay on this side. So what that's going to give us is it's going to be s squared plus 9 times x is going to equal 3s plus 4. So I moved those terms over, and then that means x is going to equal 3s plus 4 over s squared plus 9. But if we think about our table of Laplace transforms that we worked out in the last section, this is going to be better thought of as split up 3s over s squared plus 9 plus 4 over s squared plus 9. Now here, this actually matches the formula for cosine. If you remember the Laplace transform of cosine kt, that is equal to, s over s squared plus k squared, and the Laplace transform of sine kt is equal to k over s squared plus k squared, and here we are talking about k being 3. And so this is going to be equal to 3 times cosine 3t plus, now we were expecting to have a 3 on the top of this, but instead we had a 4 on the top of this. So what that means is we need to multiply it by 4/3. So x of t is going to equal 3 cosine 3t plus 4/3 sine 3t. So there's that. Now, because this was the kind of differential equation we already knew how to solve, you can actually check this by using what we would typically do. That particular differential equation by other means. In particular, it was a second order linear differential equation with constant coefficients, and it was homogeneous. So we could have found the characteristic polynomial and gone down that road. That's also going to be the case for this one, but let's notice how things are going to play out here in a way that is slightly different, at least in seeming, from the way we've done it before, but in fact it'll get us to the same place. So x double prime plus 8x prime plus 15x equals 0, and we'll start with some initial conditions of x of 0 equals 2 and x prime of 0 is equal to -3. Alright, so the first step here is to take the Laplace transform of both sides. And it is it's a linear operation, so therefore we can distribute it to each term. So the Laplace transform of x double prime plus the Laplace transform of 8x prime plus the Laplace transform of 15x is equal to 0. Laplace transform of 0 is 0. It is a linear transformation, and any linear transformation will send 0 to 0. So then this is a second order, so it's going to be s squared times x minus, now the s's count down, the derivatives count up. So it's going to be x of 0 minus, no more s's, and now x prime of 0 plus 8 times sx minus, and then the 8 will distribute, and then that'll be times x of 0. This is just an s, not an s dot or anything like that. 8s. And then plus 15x, capital X. Okay, so now let's get all the capital X's together, equals 0. Get all the capital X's together and put in numbers for the initial conditions. So s squared plus 8s plus 15, that's all times the x. And then what else do we have here? We have minus 2s for that first one, plus 3, and then minus 16 when we plug in that one, equals 0. So s squared plus 8s plus 15 times x minus 2s minus 15 equals 0. Minus 13 equals 0, I should say. Minus 13. So then x is equal to, so I'll move those over to the other side, so 2s plus 13 divided by s squared plus 8s plus 15. Now what I'll want to do is use partial fractions. And rewrite this as 2s plus 13 divided by s plus 5, s plus 3, and then what that means is a over s plus 5 plus b over s plus 3 is equal to 2s plus 13 over s plus 5, s plus 3. Multiply both sides by that common denominator, and that'll be a times s plus 3 plus b times s plus 5 is equal to 2s plus 13. Set s equal to -3, that'll cancel that one, so that'll be 0 plus b times 2 equals, and then here we're going to have -6 plus 13 is going to be +7, so b is going to equal 7 over 2. Okay, and then on this side, if s equals -5, then we're going to have a times -2 plus 0 equals, and then that's going to be -10 plus 13 is going to be +3. So a is going to equal -3/2, which means then we are now able to conclude that capital X, the Laplace transform of x, is equal to -3/2 times 1 over s plus 5 plus 7 halves times 1 over s plus 3. Now remember that the Laplace, so now we look over the table of Laplace transforms, find the one that's most similar to this, and the one that's most similar to this is e to the at, the Laplace transform of which is equal to 1 over s minus a. So then this will be an a of negative 5. This one will be an a of negative 3, but they both fit that pattern, and so that leads us to an x of t equals negative 3 halves e to the negative 5t plus 7 halves e to the negative 3t. Let's now look at a case where the partial fractions gets a little bit more intense. So here's another example. Let's say we have x double prime plus 4x is equal to cosine t, and then for initial conditions we'll say x of 0 and x prime of 0 are both equal to 0. Alright, so first we have to take the Laplace transform of both sides. So it's the Laplace transform of x double prime, where x is, remember, a function of t, plus the Laplace transform of 4x is equal to the Laplace transform of cosine of 1t, or just cosine of t. Now here what we have is s squared times capital X minus s times x of 0 minus just x prime of 0, and here what we have is plus 4 times capital X is equal to, now the cosine of t. Now this is has a k of 1, so then what we're going to be talking about here is s over s squared plus 1. A mnemonic here I like to remember is that cosine you would think would go with k on top and sine would go with s, but it's backwards. Also remember that trig is plus by t for trig, looks like a plus, versus the hyperbolic trig functions, which are a minus, but anyway. Then over here, what we've got, if I bring all the s pieces together, is an s squared plus, sorry, the x pieces together, s squared plus 4 times x minus, so it's going to be 0 times s minus 0 is equal to s over s squared plus 1. So that means that x is just going to equal s over s squared plus 1 times 1 over s squared plus 4. And again here we need partial fractions decomposition. However, it gets a little bit hairy in this particular case because we have degree 2 irreducible polynomials on the bottom, so that makes it a little bit more complicated. So that means we have to have a linear term up top, as plus b over s squared plus 1, and then plus, then it'll be cs plus d over s squared plus 4 is equal to just s over s squared plus 1 s squared plus 4. So remember, whenever you have an irreducible quadratic factor in the bottom, then that means that the partial fractions term that goes with that is going to have degree 1. So it's going to have to be a linear. So then I multiply everything by the common denominator, and that's going to be as plus b times s squared plus 4 plus cs plus d times s squared plus 1 is equal to s. Now notice that there is no even term over here, so that means all the even terms are going to have to cancel out. But let's just see what this is going to look like. So as cubed, and then we're going to have over here plus 4as plus bs squared plus 4b plus cs cubed plus cs plus ds squared plus d is equal to just s. Now from the s cubed side of things, I know that a plus c equals 0, so a equals negative c, good to know. From the s squared side of things, I know that we are going to have here b plus d equals 0, which means b equals negative d, also good to know. From the s side of things, finally, I actually have something that's not equal to 0. I have 4a plus c is equal to 1. And then from the constant terms, I know that 4b is equal to 4b plus d is equal to 0. Okay, well, putting the pieces together here, if I put this in, that's going to be minus 4d plus d equals 0. In other words, minus 3d equals 0. So in other words, d equals 0, which means b equals 0. And if I put this over here, that's going to be minus 4c plus c equals 1, which means c is going to equal negative 1/3, which means a is going to equal positive 1/3. And so altogether, what we've got here is that capital X is equal to 1/3 times, which one was this? This one was the one that's over. So it's going to be s over s squared plus 1. So the a here was the term of the s, so I can pull the 1/3 out there for convenience. And same thing, the c is the term that was going on the s of this one, so it's going to be s over s squared plus 4. Now once again here we are talking therefore about a cosine, a Laplace transform of cosine kt, which is equal to s over s squared plus k squared. And here we're talking about k equals 1, and here we're talking about k equals 2. So then that means little x of t is going to equal 1/3, and this is going to be equal to the cosine of just t, 1t, minus 1/3 times the cosine of 2t. Now, a useful fact that's going to come up in future problems is the following, so let's make a note of it. If I have the Laplace transform of t e to the at, so this is not the same as e to the at, it's t e to the at, this is equal to 1 over s minus a squared. Now we'll explore some connections here that will make this fit into more context later. But for now, let's just prove this by directly using the definition of Laplace transform. So 0 to infinity e to the minus st t e to the at dt. So now what we've got here is the same as the integral that we would ordinarily get when we were doing just e to the at, but with an extra t out front. So what I'm going to do is I'm going to make this t the u, and I'm going to make the rest of it to the du. E to the minus st, e to the at dt, which according to the rules of exponents will give us 0 to infinity t e to the a minus s times t dt. So then the u here will equal t, the du would therefore be the dt, and then the dv will be e to the a minus s t dt, which makes v equal to 1 over a minus s e to the a minus s t and so then when I keep on evaluating the integral here, so the integral then will be u times v, which is going to be t times 1 over a minus s times e to the a minus s t. That's going to be plugged in at 0 to infinity minus, and then we're going to have the integral of v du. Now as far as t is concerned, s is a constant, so it's going to be 1 over a minus s times the integral from 0 to infinity of v du, so that's going to be e to the a minus s times t dt. But this is actually going to equal just 0. So the first 0 is going to be because the exponential function overwhelms t when s is greater than a. And then minus 0. That one speaks for itself. This is going to be then minus 1 over a minus s times 1 over a minus s times e a minus s t, and then that's again going to be 0 to infinity. So then this is going to equal negative 1 over a minus s squared times, and now here when we plug in t equals infinity, once again this is going to be a 0. And then it's going to be minus 1 when t equals 0. So then that's going to equal just 1 over a minus s squared, which is the same thing as 1 over s minus a squared, although it's typically, so this is the way it would be typically written. They're the same though, because when you square something, it always becomes positive, whether it was negative or positive to start with. And here we need s to be greater than a. Okay, now for the use of this, this is just a fact that will come in handy, but now for the use of this, let's try an example that looks like this. So let's go x double prime plus 3x prime plus 2x equals t, and some initial conditions. X of 0 equals 0, x prime of 0 equals 2. Alright, well, we go to the Laplace transform here, so the Laplace transform of x double prime plus Laplace transform of 3x prime plus Laplace transform of 2x equals the Laplace transform of t. Now, Laplace transform of t, you'll recall, is equal to 1 over s. But here we have an s squared times Laplace transform of x minus s times x of 0 minus just x prime of 0. Then here we've got plus 3s x minus, that 3 distributes, x of 0 plus 2x is equal to 1 over s. So the Laplace transform of just a t is 1 over s. Actually, sorry, 1 over s squared. 1 over s squared. Laplace transform of just a constant is 1 over s squared. So then what we've got here when we collect everything that shares the x is we've got s squared plus 3s plus 2, and just the x, minus x of 0 is 0, so it's going to be 0, minus 2, minus 0. And so then what we're going to have is we're going to have x equals 2 plus 1 over s squared, and this is going to be divided by s squared plus 3s plus 2, and this is going to be s squared plus 3s plus 2 as well. So just add the 2 to both sides, and then I would divide by the factor of x there. So that's going to be then, if I combine like terms, 2s squared plus 1 divided by s squared times s squared plus 3s plus 2, which is going to equal 2s squared plus 1 times s squared times s plus 2 times s plus 1, which again is going to be an occasion for partial fractions, and so a over s squared plus b over s. So if you remember partial fractions, when you have a factor that is of a higher power, then you have to count down the powers like this. plus c over s plus 2 plus d over s plus 1 is equal to 2s squared plus 1 over s squared plus, times s plus 2 times s plus 1. So this was partial fractions when things get crazy. When you have this is partial fractions with a repeated factor. So that's why you have the a and the b. And then if you multiply everything by what it's going to take to put things where they need to be, that's going to be a times s plus 2, s plus 1, plus b times s plus 2 times s plus 1, plus c times s squared times s plus 1, plus d times s squared times s plus 2, that's equal to 2s squared plus 1. Now we can do actually very similar things to what we typically do in doing the partial fractions. We can set s equal to 0 to see what happens, and every factor of this disappears except for the a, so it's going to be a times 2 times 1 plus 0, plus 0, plus 0, plus 0 is equal to 1, so a equals 1/2. Good to know. Now what we can also do is we can plug in s equals -1. So that's going to be 0 plus 0 plus 0 plus d times 1 is equal to 3. So that means d equals 1/3. Oops, no, I mean obviously d equals 3. Okay, well then, if we want to find the value of c, we can look for what will eliminate all the rest of the terms. That would be s equals -2, which then will give us 0 from the a piece, 0 from the b piece, and then for the c, we're going to have c times -2 squared is 4 times -2 plus 1 is -1 plus 0 is equal to, over here, put in a -4, and it's going to be, and that's going to be, so -2, I mean, and it's going to be 4, 8, 9. So c is going to equal -9/4. And then when it comes time to find the last one, the b, the easiest thing to do in this case would be something like this. So we could put in the ones that we already have. 1/2, s plus 2, s plus 1, plus the mystery b that we still don't have, times s plus 2 times s plus 1, plus now the -9/4 that we have for c times s squared times s plus 1, plus the 3 for the d times s squared times s plus 2 equals 2s squared plus 1. Now notice here that the b will be the coefficient of the s cubed term. There is no s cubed term over here or over here, and the s cubed term here will be -9/4, and the s cubed term here will be 3. So we can just put them all together and say the s cubed terms, the highest degree terms here, are going to be b s cubed, and we can ignore all the lower ones, they're not going to come into play here. And then here we're going to have minus 9/4 s cubed. Then next we're going to have plus 3 s cubed, and on the right hand side there is no s cubed, so it's going to be 0. So what that means is b is going to equal, add 9/4, subtract 3, and 9/4 minus 3. So 3 is the same as 12/4. So this is going to be negative 9/4 minus 12/4 is minus 3/4. So that is going to be the b. And then if we put the pieces together to now express x, the capital X, in terms of the pieces, so a was 1/2, and that was equal to the coefficient of the 1/s squared term. b is negative 3/4, and that's going to be the 1/s term. And then we're going to have c, which was negative 9/4, and that's going to be times the 1/s plus 2 term. And then we're going to have plus the d, which was 3 times 1/s plus 1 term. And then by using the inverse Laplace transform, we have 1/2. Now the 1/2 is going to be attached then to just a t, because that's the inverse Laplace transform of 1/s squared. Here, 1/s, that's just a constant, so it's going to be minus 3/4. Here we're going to have plus negative 9/4, and this is going to be an e to the negative 2t, and plus 3 times e to the negative 1t. So notice that we actually, in this, we're able now to totally cut out the step of the complementary and partial solutions that we would get using the characteristic polynomial on the one hand, and the method of undetermined coefficients on the other. And instead, the whole problem is actually solved more or less in one swoop. Now, for systems, the Laplace transform of systems, here's a tool that will come in handy. So this is the 2x2 Cramer's rule. So if we have something like this, A, B, C, and D times x is equal to B, which we can just say B1, B2, then we can actually then break it all down into an x1 is equal to the determinant of b1, b2, b, d divided by the determinant a, b, c, d. And x2 we can just boil down into a, b1, c, b2 divided by a, b, c, and d, where these represent once again the determinants of these matrices. And what we've just done is replace the first column of the original matrix by this piece over here, replace the second column of that matrix this time by this thing over here, and then divide by the determinant of the original matrix. Now here, let's just see what this would look like as an example. Let's try to solve a system like this. So let's say what we had was x prime is equal to x plus 2y, and let's say we had y prime is equal to x plus e to the negative t, and then let's say we have x of 0 equals y of 0 equals 0 as our initial conditions. So what we'll just do is we'll apply the inverse Laplace the Laplace transform to both sides of each of these equations. So Laplace transform x prime is going to equal the Laplace transform of x plus Laplace transform of 2y. So this is going to be s times x minus x naught. It's going to equal x plus 2, and now we're talking about capital Y. Meanwhile, on the y side of things, the Laplace transform of y prime would equal the Laplace transform of x plus the Laplace transform of e to the minus t, which would be then s times y, and then what we will have here minus y0 is equal to capital X plus, and then this is 1 over s plus 1. Now, if we were to collect all the x's and y's to one side, well, and I guess the x naught is equal to just 0, so let's just go ahead and say sx equals x plus 2y, and sy is equal to x plus 1 over s plus 1. Then what we would want to do is turn this back into a system now for capital X and capital Y. So that's going to be then capital X times s minus 1 minus 2y equals 0. And then alternative, and then on the other hand over here, what we could have is negative x plus sy is equal to 1 over s plus 1. And so what we could then do is treat this system as s minus 1, negative 2, and then negative 1, and then s times capital X, capital Y is equal to 0 and 1 over s plus 1. And now what we can do is use Cramer's rule. Which would tell us that x would equal, capital X that is, the determinant. Now I just replace the first column with this column. 1 over s plus 1. Sorry, 0, and 1 over s plus 1, and then negative 2 and s divided by the determinant of the original thing, s minus 1, negative 2, negative 1, and s. So then using the property of or just using the typical definition of a determinant, what I will have here is 0 times s plus 2 over s plus 1 divided by s times s minus 1 and then minus 2. So that's going to equal 2 over s plus 1 times s squared minus s minus 2 which is going to equal 2 over s plus 1 squared s minus 2. Meanwhile, capital Y is going to equal then, according to Cramer's rule, now it's going to be the second column that gets replaced. So it's going to be s minus 1 and negative 1 still for the first column, and now it's going to be 0 and 1 over s plus 1 for the second one. And then on the bottom, we're going to have still s minus 1, negative 2, negative 1, and s. So it's going to now be s minus 1 over s plus 1 divided by, and it's going to be the same thing, s times s minus 1, minus 2, minus negative 2 times negative 1. So then that's going to be s minus 1 divided by, bring the s plus 1 down, times s squared minus s minus 2, which is going to be s minus 1 over s plus 1 squared times s minus 2. So now, all we have to do is a little bit of partial fractions, and we'll be able to figure out then how to break that into two pieces that we can then do the inverse Laplace transform of. So if x is equal to 2 over s plus 1 squared s minus 2, then a over s plus 1 squared plus b over s plus 1 plus c over s minus 2 equals 2 over s plus 1 squared times s minus 2. So that's going to be the partial fractions that we're going to want to apply here. And so what that means is, if we multiply by a common denominator, we're going to have a times s minus 2 plus b times s plus 1 times s minus 2 plus c times s plus 1 squared is going to equal just 2. Now here we can do similar stuff to what we usually do. So set s equals negative 1. That'll clear out everything except for the a. So then that's going to be a times negative 1 minus 2 is negative 3. And that equals 2. So that means a equals negative 2/3. And then as far as the c, we can get that by setting s equal to 2, and then that's going to be 0 plus 0, and then c times 9 is equal to 2. And so c equals 2/9. And then for finding the b, we can just do a similar thing to what we've done before. So for the b, so we have negative 2/3 times s minus 2 plus mystery b times s plus 1 times s minus 2 plus 2/9 times s plus 1 squared is equal to 2. So if I take the s squared terms, then there will be none over there. It's going to be b s squared plus 2/9 s squared equals 0. So b has to equal negative 2/9. And so then finally we have capital X is equal to negative 1 over s plus 1 squared plus negative 2 ninths times 1 over s plus 1 plus, then c was positive 2 ninths times 1 over s minus 2. And here, sorry, I went a little bit, jumped the gun a little bit on this one, but if you remember, this one is, this one fits the Laplace transform pattern for t e to the at, which equals 1 over s minus a squared. This one fits the pattern Laplace transform of e to the at just equals, and actually this one does too, 1 over s minus a. And so putting these pieces together here, we can see that little x of t is going to equal, and what we're going to get is going to be negative t e to the negative 1 t. So negative t e to the negative t minus 2 ninths e to the negative t, and then plus 2 ninths e to the 2t. And as for the y, it would just be a similar process. So for the y, capital Y, this was equal to s minus 1 over s plus 1 squared times s minus 2. And so once again, we're going to go with a over s plus 1 squared plus b over s plus 1 plus c over s minus 2 is equal to s minus 1 over s squared, s plus 1 squared s minus 2, which gives us the same basic equation as before, just a different thing on the right side. So a times s minus 2 plus b times s plus 1 times s minus 2 plus c times s plus 1 squared is equal to s minus 1. So if s equals negative 1, then we're going to have a times negative 3 as before is equal to, now it's going to be a negative 2. So a equals 2/3. And if I have s equals 2 as before, I'm going to have c times 9, so the right hand side, left hand side will all be the same. It's only the right hand side that could change. Equals 2 minus 1 is 1, so then c equals 1/9. And then by the same logic as what led to before, we're going to have b s squared plus 1/9 s squared equals 0, so that means b equals negative 1/9. So what that means is that capital Y is going to equal 2/3. Alright, everyone hold on 1 second. Scroll back up a little bit here. For some reason, I put just negative instead of negative 2/3 on that x. You've probably all been scratching your heads, wondering how that came to be, and the reason was the oldest mathematical mistake in the book, a boneheaded typo. And then that would mean this is also negative 2/3 right there. So if you've been scratching your head for the last couple minutes, wondering how that 2/3 was lost, you're right. How was that lost? Indeed. Okay. So now back to the back in flow here. We're now on the y, and this is now positive 2/3, 1 over s plus 1 squared. The b is equal to negative 1/9 times 1 over s plus 1, and c is equal to positive 1/9 times 1 over s minus 2. So then that means that little y of t we can now find to be positive 2/3 t e to the negative t, by the same logic as before, minus 1/9 e to the minus t plus 1/9 e to the 2t. So x and y are then negative 2/3 t e to the negative t minus 2/9 e to the negative t plus 2/9 e to the 2t, and y of t is what we just found. So 2/3 t e to the negative t minus 1/9 e to the minus t plus 1/9 e to the 2t. So notice that was a system that was not an autonomous system, which is beyond our capabilities actually up until just now. So that was actually pushing the boundaries of what we could have done according to the techniques that we've developed so far in this course. So there is a little bit past what were capable of doing before. Now, what if we really pushed the envelope of what we were capable of doing before and see what we can do if it's actually a higher order system of differential equations? So as our next example, let's take a look at x double prime plus 2x plus 4y equals 0, and y double prime plus x plus 2y equals 0, with initial conditions of x of 0 equals y of 0 equals 0, x prime of 0 equals y prime of 0, which equals, say, -1. Okay, so here's another initial value problem, but it's a system of order 2. So we have is the Laplace transform of x double prime plus Laplace transform of 2x plus Laplace transform of 4y equals 0. Let's just take this down the road. So it's going to be s squared times capital X minus s times x of 0 minus x prime of 0, and then plus 2 times x plus 4 times y equals 0. Now putting in the numbers that we have here and collecting all the x terms and the y terms. So this is equal to just 0, This one is equal to -1. So altogether here, what we're going to have is s squared plus 2 times x plus 4 times y is equal to -1. I'll just add x prime 0 to both sides, and that will be the first one. Okay. Also, the Laplace transform of y double prime plus the Laplace transform of x plus the Laplace transform of 2y equals 0 will lead us to s squared capital Y minus s y of 0 minus y prime of 0 plus capital X plus 2 times capital Y equals 0. So again, that's not going to matter because of the initial condition. So combining the things, we're going to have x plus s squared plus 2 times capital Y, and this one is going to equal, again, -1. So then, what that leaves us with is s squared plus 2x plus 4y equals -1, and x plus s squared plus 2y also equals -1, which then leads us to the matrix version of this, which is s squared plus 2, 4, 1, s squared plus 2 times x and y equals -1, -1. Hi everyone, this is Scott. I'm just cutting in here. This next page of notes, there was a slight mistake right up at the very beginning. A student noticed it, and now I'm correcting the slight mistake. So if you already watched this video, please note the slight correction here. If you have not yet watched this video, then forget I said anything. So in finding the x, we use Cramer's rule. So we put in the place of the first column of the top, the b, the b1, b2, and then we leave the second column as it was. We take the determinant of that and we divide by the determinant of the original matrix. S squared plus 2, 4, 1, and s squared plus 2. Now here we're about to see where the original mistake happened. So up on the top, when we take that determinant, it's going to be -1 times s squared plus 2, and then plus 4 minus -4. On the bottom, what we're going to have is going to be s squared plus 2 times s squared plus 2, all minus 4. And so up on the top, that's going to be -s squared minus 2 plus 4. That's the mistake before. We had in the previous original version of this video, there was an incorrect term right up here. And then down below, we're going to have s to the 4th plus 4s squared plus 4 minus 4. So up in the original version, there was a -4s right here, but that should not have been there. It came from me glancing down at this one and wrongly anticipating what the terms were going to be. A classic blunder. Okay, so up here then, what we're going to be talking about is -s squared plus 2 So there's no minus 4s term. And downstairs, s to the 4th plus 4s squared, which we can then factor and make negative s squared plus 2 s squared, and then s squared plus 4. So now, once again, we're going to need to use partial fractions decomposition to break this up, because it is not currently in a form that we can work with as yet. We'll learn some other tricks for perhaps dealing with things like that, but for now, what we'll do is we'll fall back on our old friend, partial fractions decomposition. So we're going to have an a over s squared plus b over s plus cs plus d, since this is an irreducible quadratic. It's got to have degree 1 less on the top, over s squared plus 4, and that has to end up equaling negative s squared plus 2 over s squared times s squared plus 4. So then, if we multiply everything by the common denominator that we would have, we're going to have a times s squared plus 4 plus b times s squared plus 4 plus cs plus d times s squared. And that's going to equal negative s squared plus 2. Now we can do things like set s equal to 0. That'll give us, that's basically the equivalent, by the way, of just peeling out the constant terms. That's going to give us a times 4 equals 2, leading us to a equals 1/2. So there's that. And then for the other pieces, we can just look at some of the big terms here. So there's going to be an s cubed. The s cubed terms are going to leave us where there's going to come from. It's going to be bs cubed, and then the other s cubed is going to be from over there. cs cubed is equal to 0. S cubed, which means that b equals negative c. And there's an s squared term. And from the s squared terms, we are going to be getting an a. So we're going to be getting an as squared. We're going to have a ds squared is equal to negative s squared. But a we already know is 1/2. So what that means is that if we subtract 1/2 from both sides, we're going to have d equals negative 3/2. And so there's that. And now for the s terms. So this is where it's going to be changed from version 1.0 of this video. So for the s terms, those are going to be coming from right here, and that's going to be the only purely s term. It's going to be b times s times 4 is equal to just 0 on that side. So that means that, I guess 0s. So b now equals 0. Okay. Now putting the pieces into play then, what that means is that capital X is going to equal 1/2, 1 over s squared. And then there's going, and so then that means c also equals 0 from up here. And then so there's not going to be a b term, there's not going to be a c term, there's only going to be a d term. So plus negative 3/2, and that's 1 over s squared plus 4. So we're now missing the two terms that were in the middle here, incorrectly, first time out the gate. And then that means if I do the inverse Laplace transform of both of these, what we're going to have is 1/2 t. And then here it's going to be minus. Well, this matches closest to the sign. However, the sign is supposed to have a factor of k on the top. This one does not. K here would be 2. And Laplace transform of sine kt k over s squared plus k squared. So we needed to have this is going to be minus 3 halves times 3 halves times an extra 1 half times an extra 1 half sine 2t, which is going to then be 1 half t minus 3/4 sine 2t. And the reason here was therefore then that the Laplace inverse of 1 over s squared plus 4 is going to be 1 half sine 2t. Should have added 2. Okay, so then that finally gives us our x of t. And now we can do what we can to find the y by basically the same process. It is a complicated process, no question about it. But it is a process that goes like clockwork. So once again, we take the, so we're going to use Cramer's rule here, and the system that we're talking about looks like this. So now it's going to be s squared plus 2 and 1 left alone, -1, -1 going into the second column, Cramer's rule. And then in the bottom it's going to be s squared plus 2 for 1, s squared plus 2. So then that's going to be, so then that's going to give us negative s squared plus 2 plus 1 divided by s squared plus 2 squared minus 4, which is very similar to what we had before, but now minus s squared minus 1 over s squared times s squared plus 4. But this is going to then break down in exactly the same way as before. So we're going to have then a over s squared plus b over s plus cs plus d over s squared plus 4 is now going to equal negative s squared minus 1 over s squared times s squared plus 4. And so then we're going to have the same breakdown as we had before, a times s squared plus 4 plus b times s squared plus 4 plus cs plus d times s squared is equal to negative s squared minus 1. And now, once again, s equals 0 gives us the same sort of operation as before, but now it's going to be a times 4 is equal to negative 1. So a equals negative 1/4. And then we can go with the s cubed terms again. Just follow our footsteps from previously. So we again have a bs cubed, so that's going to be the first time there's going to be an s cubed. and a cs cubed is equal to 0, so b equals negative c. We can do an s squared. We look at the s squared terms, it's going to be negative 1/4 s squared plus 4b s squared. No, sorry, that's not going to be there. Plus d s squared is equal to negative 1. So then, what is it? D equals negative 1 plus 1/4. So that's going to be negative 3/4. Okay. So then we need still the c, so we can get that from the s terms. So from the a, there's not going to be any s terms there. From the b, there will. So there's going to be b times s times 4. And then from and then there's not going to be any s term over there, so and there's no s term over there, so that equals 0. So b equals 0, which means c equals 0, which means that then y is going to equal negative 1/4 times 1 over s squared plus, and then just the d is negative 3/4 times 1 over s squared plus 4, which means that we are going to have negative 1/4 t, sorry, so little y, can be negative 1/4 t minus, and then this will be 3/8 sine 2t, because the Laplace transform of sine 2t would be a 2 up there, so I need to divide by an extra 2 to make it work. Alright, and that's how we do that. Now the last topic of the section that we're going to be talking about now is transforms of integrals. So this is a tool that can make our lives a little easier, save us a little bit of partial fractions, and it has to do with the following observation. We can take what we know about derivatives and run it in reverse. So the Laplace transform of the antiderivative, which we'll express in terms of the integral function, the integral from 0 to t of f, and then you need a new letter, so say tau d tau. So this is equal to, if you think about differentiating, it brings out a factor of s. This one instead brings out a factor of 1 over s. So it's 1 over s times the Laplace transform of f of t. In other words, is equal to just f of s divided by s. So in other words, if we have something that looks like one that we know but is divided by s, and we're trying to take the inverse Laplace transform of that, so we know what this would have been like if it didn't have a factor of s on the bottom. This is then going to be just the antiderivative expressed in this manner of f of tau d tau. In other words, the antiderivative. the antiderivative of f. So, for example, let's take something we know, like this. So f of, let's say we wanted to find the inverse Laplace transform of f of s equals 3 over s times s plus 5. Okay. So let's say then that that g of s is equal to the 1 over s plus 5. Then what we've got here is 1 over s times g of s. So then the inverse Laplace of g of s divided by s would be, and notice that this would mean then that g of t would be equal to e to the negative 5t. This is a famous one. So then this would be equal to the integral from 0 to t of e to the negative 5 tau d tau, which would be negative 1/5 e to the negative 5 tau, plug in 0, plug in t, and so plugging in the t is going to be negative 1/5 e to the negative 5 t, plug in the 0, and it's going to be minus negative 1/5, so in other words plus 1/5. So then what we've got here is then the inverse Laplace of 3 over s times s plus 5 is equal to 3 times negative 1/5 e to the negative 5t plus 1/5, which equals negative 3/5 e to the negative 5t plus 3/5. And this problem also could have been done by using partial fractions, but also this way. Let's try one where it has an extra factor of s. So let's say we wanted an inverse Laplace transform of something like f of s, which equals 1 over s squared times s squared minus 9. Now we could do partial fractions here, no law against that. However, we know that this looks a lot like something from our catalog. So let's say that g of s is equal to just the 1 over s squared minus 9. That would then make g of t equal to, so here what we've got is something that resembles the hyperbolic sine function, but it's off by a factor of 1 over k. So this is going to be 1/3 sinh 3t. Okay, well then the inverse Laplace transform of 1 over s times s squared minus 9 would be the integral from 0 to t of 1/3 sinh 3 tau d tau, and the integral of sinh is equal to cosh, so that's going to be 1/3 times 1/3 times cosh of tau, tau going 0 and t, and so this is going to be 1/9 cosh t, and then the hyperbolic cosine of 0 is equal to 1, so minus 1/9. So that gets us there, but then we need to go one step further. So if I want s squared times s minus 9, it's going to equal the integral from 0 to t of 1/9 cosh, should be 3 t, cosh 3t minus 1/9, sorry, 3 tau, 1/9 d tau. So that's going to be 1/27 sinh 3t minus 1/9 t, all being evaluated on the one hand at 0 and t. And so then what we've got is 1/27 sinh 3t minus 1/9 t, and then if I plug in 0, it's going to be 0 and 0. Sinh 3t. 1/27 sinh 3t minus 1/9 t will be our final answer there. And again, that could have been something that we could have gotten by means of partial fractions. But this saved us that. So you can't have everything, but we can at least replace some partial fractions with integration. So obviously anti-differentiating is itself a complicated enough process, but you gotta pick one or the other. Alright, well, on that note, let's go ahead and call that a lesson. So that was section 7.2. Join me next time for the next episode of Math 256. Till then, bye.